Cool.
Hey everyone, we have Sunny from Sikka and Dev from Tendermint off screen. They'll be doing a talk on preventing front running through privacy in the mempool. And I'll let them take it from here. Can you guys just confirm you can hear them once they start talking?
Hello, can people hear me? I'm going to assume so, unless anyone lets me know to the contrary. Welcome to this talk. Unlike, most of the other talks today, which were probably mostly around like zero knowledge proofs and privacy at like the state machine level, we're going to be talking more about sort of another use of privacy, which is to prevent front running, which is really a really important piece of making blockchains mature infrastructure for financial applications. So, to begin with, we just want to go ahead and give a rundown of, first off, what even is this front running problem? So let's say we're not in the blockchain world. We're just in traditional finance. You want to you're making a stock trade, right? So what you'll normally do is you will set how front running would work in the normal world is you would send your stock order to your broker, and then the broker is supposed to submit your trade on the exchange for you. And front running is when your broker goes ahead and puts his own order in front of yours in order to profit from it. So, as an example, if you were trying to buy 1 million shares of, of syndicate company, right? And that would drive up the price by like $5. The broker would put his trade in front of yours, and then so that way to buy some of the same shares as you, and so then he can sell them as soon as after your order and take a profit off of this. And so this is there are regulations and stuff around this, but it's still really a common practice. Like the common other for you may have heard the term like buying order flow, like what hedge funds do with Robinhood, for example. These are all like sort of examples of front running. And so what would front running be in the blockchain context? What we would have is, in a blockchain, we have this sort of validator network. Obviously, my background is in Tendermint. And so I approach things from a very Tendermint standpoint, but, you can imagine this being a network of miners as well. And what happens in a blockchain is you make a transaction and you send it into the network. And these get added, propagated through the network and added into people's mempool. But, the key here is that what happens is there is one person who has to propose the block. So while there's many different validators or miners, fundamentally one of them has to be the person to, propose the block to the network, and the other miners or validators either, if it's a BFT protocol, they'll continue to vote on top of it, or if it's a proof of work protocol, they'll continue to mine on top of that block. But the problem is that whoever that proposer is, for this example, let's assume it's this middle validator. That's the logo for Sikka. But so, Sikka has two different orders in its mempool. The thing is, it could go ahead and insert its own order into the mempool. It realizes, hey, Alice, sent this transaction. Maybe there's a way for us to profit off of it. So we're going to add our own transaction. And so when, see this middle transaction here, Sikka just added our own transaction into this thing, and because we can profit off of this. And, we can go ahead and propagate the block, and, it'll come to consensus, and we lock in the block. And, what you could think about is this is basically like the proposer is essentially very equivalent to your broker in the traditional market sense, where, they are basically get the first rights to like see your order and like submit it to the rest of the network. And so this leads to this like front running problem. And the generalized version of this is, there's this term called miner extractable value, or MEV for short. You may have heard this term, thrown around as big buzzword these days. A couple of our friends that they work, there's this blog post about entering the dark forest and like generalized front running and all these things. And so really what we want to do is, how do we make it so we can like minimize this MEV? the naive solution would be saying, hey, what if we just do ordering before consensus? And there's a couple of different projects that are attempting to do this. And what they say is, hey, what if Alice sends her transaction to the validator or proposer, and the proposer gives you back a signed acknowledgement saying, hey, okay, I acknowledge that you're going to be transaction number 2. And then when the proposer makes the block, the proposer actually puts Alice's transaction as transaction number 3. In that case, Alice can take her signed acknowledgement, submit it to the chain, and it will, punish or slash or do something with the validator because it, this cryptographic evidence that she was supposed to be transaction number 2 in that block. However, there's issues with this. One, there are like centralization. You can't always assume that one person is always going to be the proposer, right? The proposer is supposed to change, and so it becomes very hard to coordinate whose acknowledgements are valid, because you might have gotten an acknowledgement from Sikka that you'd be transaction number 2, but it turns out Sikka failed to propose a block. It goes to someone else, and now your acknowledgement is not valid. That acknowledgement only held Sikka to account, no one else. On top of that, it creates these lagging concerns. Also, it doesn't really solve the problem because, Alice can send a transaction to Sikka, and Sikka can just say, okay, here, you're transaction number 3. And when it's time to propose the block, Sikka can just, go ahead and insert their own transaction in. And, if there's nothing for them to profit off of, they could just insert a dummy transaction in slot number 2, just as a way to push Alice's transaction number 3 so they're unslashable. So this is obviously a naive solution. It doesn't really work that well. Other variants of this are like, projects that say, oh, if we increase or decrease the block time, make blocks faster, this solves the problem. If you think about it, that's sort of just a variant of this claim where it's like, it heavily depends on like the honesty assumptions of the proposal. What you could do to solve this is do things like batch mechanisms. So if you're building a DEX, instead of doing like transaction numbers, you use batch numbers, and you do like batch execution for order books. But we don't want to go too far into this. But the key thing here is it's not very generalizable for arbitrary execution. And so this is why people propose things like MEV auctions, but they don't actually prevent front running. It just builds a platform to do front running and then charges a tax on it. And that tax is basically at the expense of users. So, this is not a great solution. This is not providing value to the users. So what we want to do is solve this MEV problem. And so how are we going to do it? But before we go figure out what we're going to do, let's first categorize the different types of MEV. And so we'd say there's 3 sort of main types of MEV that we want to focus on. And they kind of fall into this like 2x2 matrix. There's one where you are based on someone else's transaction. Well, okay, before that, actually, there's one where there's relative ordering and there's absolute ordering. A relative front running attack would be you see another transaction and you say, hey, I want to be the first transaction in front of this other person. Or I want to, it also includes things like backrunning, which I want to be the first transaction after this other transaction. And so this is like this relative ordering thing. But then you also want to solve absolute ordering, which is, let's say you're not trying to front run a specific transaction, but rather, there's some arbitrage opportunity at the end of the last block, and you want to be the first transaction in the block. So you are the one who can execute it before anyone else can. See, here you're not really like trying to be in front relative, like, I want to be before someone else's block. You just want to make sure you're the first in a block. And so this we'd call absolute front running, where you're not front running any one transaction. And so, for absolute front running, there's like, you can have it so it's not based on another person's transaction data, or you could have it so it is based on someone else's transaction data. What we mean by it is based on someone else's transaction data, this is like this dark forest attack that Dan Robinson wrote about, where you're just constantly scanning the mempool, seeing what transactions other people are doing, and trying just swapping out their addresses for yours, so and seeing if it makes you a profit. So like if there's like a white hat transaction that can be made to like save someone money or something, you could just black hat it by looking at that transaction, replacing it with your address, and then stealing the money for yourself. So this absolute ordering can be based on both. Relative ordering, obviously, it doesn't really make sense for it to not be based on someone else's transaction data. So it has to be based on transaction data. And this is what we normally consider the front running. So to start with, we're going to start by solving this like normal front running piece, and then we'll come back to solving absolute ordering. So this is what we're going to start by solving. And what we're going to say is there's essentially going to be three ways to do this. We're going to have SGX, TimeLock Encryption, and threshold encryption. But the key piece that joins all these techniques together is essentially the idea is we encrypt transactions in the mempool. So you want transactions to be unreadable in the mempool, and we only decrypt them after they've been committed to a block. So Alice will go ahead, this blurred out transaction, you can't really see what's going on. Alice will go ahead and submit this transaction to the proposer. The proposer has in the mempool, it's unreadable to the proposer. The proposer will go ahead and have all these transactions in the mempool. They'll go ahead and include the create a block with all these encrypted transactions and spread it to the network and get it locked in. So it has to come to consensus on the block. Then we're going to use one of these three encryption techniques basically to do magic, and it will decrypt the transactions, and then we can execute them. So basically, we're separating the proposer, their job is to include transactions in a block, but they don't get to know what the content of those transactions is. And so what we're going to do is go ahead and kind of walk through these three different techniques and kind of give some of the pros and cons and compare how they differ. So the first one is the SGX based model. How it works is every miner or validator will have an SGX, and they everyone's SGX will have the same private key, decryption key in it. So, we would need a protocol so that every time a new validator shows up, how you can share the decryption key with that validator. And, this is out of scope for this, but, there's a lot of there's a lot of projects that have worked on this already. And then what you're going to do is when you create a transaction, you encrypt your transaction to the shared SGX key. And then the SGX hardware can verify certain properties about validity of the transaction. Even if it's encrypted, it can verify it within the SGX without leaking anything about the transaction. It can verify that, the fees are sufficient. It can verify that the signatures are valid and whatnot. And what it can do is it could output a block hash for validators to come to consensus on. And this will be in the BFT context. So a BFT consensus. So, it will say, okay, validators, here's the block that you're supposed to come to consensus on, come to consensus. Once you've come to consensus on it, you can submit a proof of consensus. So, protocols like Tendermint and most BFT protocols, you can have a proof showing, hey, this block is finalized now. You can submit that to the SGX, which will then return the decrypted transactions that can be executed. You can also do this with Nakamoto consensus, like a proof of work today. Here, in Nakamoto consensus, there isn't a finality proof because, there's not, unlike BFT, you can't say that, hey, this transaction is finalized. But what you can do is have every miner, you send encrypted transactions to the miner's SGX. The SGX lets the miner know, here's the block hash that you're supposed to mine on. If the miner finds a valid block hash, they can then submit that to the SGX, and the SGX will say, okay, this is good enough. Now I'll give you the actual transaction data that you were mining on. This is kind of cool because this can, this actually doesn't require any protocol changes. You could do this today. Any mining pool can go ahead and set up a service today where they say, hey, if you want to submit encrypted transactions, you can just submit them to our pool because we support this SGX protocol. Obviously, the problem here is the miner could rehash, start mining again after decrypting transactions. So, they do all this mining work to decrypt to get the data from the SGX, and then they could say, hey, there's a really good opportunity here, and let's go ahead and I want to build a new block where I insert my own transaction in front of this. This would cost them one block's worth of rewards in order to do it. But maybe the profit here is valuable enough to make it worth it. And so this is one of the cons of this process. So given this, what are the pros here? It can be easily included as an opt-in feature. It doesn't need any protocol level changes. The cons here is it's not really a great security trade-off. Breaking an SGX has some cost, maybe it's $1 million, maybe it's $10 million. We see every couple of months we get new papers out about exploits in the SGX system. And so the idea is once the value of the MEV exceeds this cost of exploit, you can safely assume that some mining pool or someone has put in the funding to break the SGX, and they are front running again because it is a profitable activity. Also, this does has a cost to miner efficiency because mining pools spend a lot of time optimizing on every last detail to make sure that they're propagating blocks absolute fastest. And so having to talk to the SGX to give the SGX computation isn't very fast. It definitely causes incurs a cost to the miners that opt into this system, and that would have to be made up for by the fees paid by users. So here the MEV security. What's the security model? It's basically whatever the cost is to break one SGX. And what's key here is you don't have to break. As soon as one SGX is broken, the privacy and front running of all of this entire system is broken. It has really good execution delay. It blocks. Transaction will be executed immediately, and the consensus delay is it doesn't have that big of a impact. It delays the miner a little bit, so we'll give that a medium. But the other nice piece is like we mentioned, technically there's no protocol changes required, which is a really valuable property if you're trying to add this into an existing layer 1 system like Ethereum. Moving on to the next solution is what TimeLock encryption. So what we do here is we use a primitive called TimeLock cryptography, where basically you can think of it as if you're basically encrypting a message with a very weak encryption that if people can just sort of if you do a sufficient amount of work, you can decrypt the message, and it's non-parallelizable, which is the key. And so anyone can go ahead and do that. And so what you can do is you can encrypt the message and such that it is only decryptable after some amount of time. Let's say it's 5 minutes or something. Then what you can do is you can say, okay, transactions are included now at block N, but then they have to be included in a block by a block that's 7 minutes after block N, but it only takes 5 minutes to actually do the decryption. So this makes it such that anyone can do the all the miners, once they get a block, they start to do all the decryption of all the transactions. And if you're the validator or miner who wants to propose block N+7, you must include the decryption of the transactions from block N. And this kind of prevents the front running, and it makes it so it's very easy for any individual to decrypt, but it takes some amount of time. And so the benefit here is it does prevent against front running, but it adds a notable delay to transaction execution, because if transactions are, if you include a transaction at block N, the earliest that it could be actually executed is N+5. And so this is really not great for UX, as you can imagine. When people, it's already a big UX hurdle today when people want to do a Bitcoin transaction and it doesn't get executed until 10 minutes later. We want to minimize the amount of time. And this is one of like the big pros of Ethereum, that, you know, the delay between execution and like, you know, creating a transaction is pretty small. And this is one of the big UX features that has really helped out Ethereum. And we need this delay to be sufficiently long because there'll always be like some level of variance in the amount of time that like the time lock takes to unlock, and how long it takes a transaction to be included in a block. And so this basically makes it so the time lock can't be on the order of seconds. It needs to be on the order of minutes. Secondly, another sort of con of this is all transactions have to use time lock crypto. So like you can't say that in the SGX model, for example, in the previous model, you could say like, hey, I want my transaction to be protected, so I'm going to encrypt my transaction to the SGX. But if I'm just doing a transaction that I don't care if someone front runs me, I don't have to use this like protocol. But in the time lock crypto, to make it actually work against front running, everyone has to do it. And so it's not like you can opt into having the delayed transaction execution. You must do the delayed transaction execution, which is once again just really, really poor UX. And so so as I mentioned here, so the execution delay is quite high, and the amount of security you have is basically a trade-off against the delay. So if you want the trade-off, if you want the delay to be 1 minute, right? Then you have to be able to just prevent a transaction from being included in a block for 1 minute until you can figure out what it says. Well, if you have the execution delay be like 1 hour, you'd have to prevent the block from being included, the transaction from being included in the block for at least an hour. And it increases the security of the system, but at the trade-off of the delay. And then finally, it doesn't have much impact on consensus time, essentially negligible. So finally, this is the third solution is threshold decryption, which is personally the one that we are the most excited about. How this works is, you need to use a protocol in which execution of transactions happens in the block after they are included. Essentially, you need some level of pipelining, which Tendermint sort of has built in already. And what you do is every validator will have a share of a BLS threshold decryption key. And the key is such that any 2/3 of the validator set can decrypt the data. And you want this to basically match whatever your safety threshold is for your consensus protocol. So if your consensus, most consensus protocols usually use 2/3, but if your consensus protocol was 3/4, you'd want the threshold key to be at the same threshold. And so what would happen is you could have it such that, in Tendermint consensus or most BFT consensus protocols, every validator needs to include some data, include their votes on a block. So, you have one proposer make a block proposal, and then all the validators vote on it, and you need at least 2/3 of them. You need the signed votes of at least 2/3 of them in order for the block to be finalized. So what we can do is say that along with the votes, every validator needs to include their decryption share. And you can make it so that essentially this makes it so that transaction decryption happens in lockstep with consensus. So transactions can't be decrypted without a block being finalized, but at the same time, a block can't be finalized without the transactions being decryptable. And so this allows you to go ahead and, as soon as the block is finalized, we have all the data we need in order to decrypt the transactions and execute them. One of the issues here is that the size of the data could be quite large. So, let's say the total data that you're trying to threshold decrypt is n bytes. That means each decryption share must also be n bytes. So, and if the n is high, this could cause a pretty large overhead, because let's say, a transaction, let's say a block included 1 megabyte worth of transaction data. This means every validator, let's say there's 100 validators, every validator would have to include 1 megabyte of data in their consensus votes. And this is not really, this causes way too high of an overhead. So the solution we have for this is that transactions are not encrypted with their threshold key directly. Instead, they're encrypted with a 128-bit symmetric key. We can probably even reduce this, but we'll go with 128-bit for security right now. But it can probably be reduced because these are ephemeral one-time use keys that we're not going to use again, and they'll be they should be made use of pretty quickly. And so what happens is these symmetric keys then are encrypted to the threshold key and included with the transactions. So now this means that, so essentially, a transaction is encrypted with a symmetric key. Symmetric keys are encrypted to the threshold key. So now validators only have to the size of each decryption share is the size of all the symmetric keys put together. Each symmetric key would have one. So each transaction has 1 symmetric key. So the size of each decryption share would still be linear in the number of transactions, but it would be a constant multiple rather than being arbitrarily based on the size of the transaction. And so this massively reduces the network bandwidth overhead, which will make this a much more feasible protocol for actual usage. And finally, in the mempool, the fees cannot be encrypted because you need to be able to pay for the decryption. And this requires, in order to pay the fees, you need to know which account is paying the fees. And this could leak information which could lead to an edge. But, you can solve this using more traditional on-chain privacy stuff. So if you had a zonal shielded pool on this blockchain, you could hide all these transactions. You can hide the source of the funds for the fees. And then the size of transaction data could also leak data about the transaction, but this could be, pretty easily solved through padding schemes. With the threshold encryption, we essentially get equivalent security as consensus. So, in consensus, you need to control 2/3 of stake or voting power in order to break consensus. You get the same security here. You need to break 2/3 of voting power in order to be able to front run transactions and figure out what they say before executing them. The execution delay is extremely small. You get a 1 block delay, and the consensus overhead is it's medium. Like I said, it's still linear, but it's not that bad because we've massively decreased the amount of overhead. And one important caveat for the threshold encryption is it really only works in classical BFT consensus protocols. So you can't really use this with Nakamoto consensus, which is proof of work, or many protocols like, Ouroboros and whatnot. You need to use a protocol like Tendermint or Hot Stuff or Honey Badger, any of these protocols that basically have all validators participating before a block is finalized. So yes, using any of these solutions, particularly the threshold decryption one we propose, you kind of solve the ability to front run someone based on their transaction data because you can't see their transaction data. But now what about this blind front running where, you don't care what anyone else's transaction on the block. You just want to make sure you're the first transaction in a block. So here we have a simple solution, or part one of a 2-step solution. So part one is pretty simple. We just randomize the order in which transactions are executed. So even if, so like I mentioned, you want a block producer, the proposer, or the miner, they can guarantee that they're the first transaction in a block. So all we have to say is, once we decrypt all the transactions, we can go ahead and, hash them in order to create some random number that was unpredictable. And we use that random number to rearrange all the transactions. And what this does is the block proposal only really is determining transaction inclusion, not ordering. So, we have, using the threshold decryption scheme we talked about, we take all the encrypted transactions and we decrypt them. But then the next step is, we tornado them and rearrange them based off of some random number and reorder them, and they get executed that way. So now it's basically impossible for a proposer to say, hey, I want to be the first transaction in a block. But there is one issue here. What if the proposer says, my transaction is the only transaction in a block? They just, if they're the only transaction in a block, even if we randomize them, they still end up being the first transaction on block. How do we solve this? We use a system called, we're working on the name for this, but we're calling it joint proposals for now, where once again, the problem is the block proposer can censor all other transactions and only include their own transaction in a block. The solution is in the votes of the finalizing the previous block, we allow each validator to include a constant number of transactions.
Hey, Sunny, we're out of time, actually.
Oh, really?
Yes.
Oh, my bad. Okay. Yeah, okay.
Do you want to share your slides somewhere or give a link and someone can follow up with you guys?
Yeah, for sure. That would be great. That was my last slide anyway. So thank you guys all for listening. And if you guys are interested in learning more, please reach out to us. I'm Sunny at Sikka.tech, and we're excited to work with people on killing MEV and making the mempool a safe place for everyone.
Awesome. Thanks, Sunny. This was great.